This video will cover section 10.4, hyperbolas, and this is another one of the conic sections. So the objectives will be to write the equations of hyperbolas in standard form, to find the asymptotes of and graph hyperbolas, and also to use the properties of hyperbolas to solve real-life problems. And at the end, we are going to go over how to classify conics from their general equation. So remember, for every conic that we have discussed, we have gone over the standard form. And so at the end of this section, we will summarize those with their general form, including the circle. So as an introduction, hyperbola, the definition is similar to the one of an ellipse. For an ellipse, we add the distances that that are from the foci into a point on the hyperbola. So something like that. Let's say the foci here, and we pick a point. And so if we trace the distance from one to the other and we add them, it will always be the same as for any other point, tracing it to the those 2 points, to the foci. Remember, foci is the plural for focus. So that was where the focus was. So those the addition of those two distances, not that they're equal, but the addition of them will tell us that they are that the distance will be constant, meaning that it will be equal. So with the ellipse, we also have something like that, but in this case, we're not gonna look at the sum, but at the difference. So it means that we will be subtracting, and we're gonna use the absolute value just to make sure, because it's distance, so all distances are positive. So when we subtract those distances, the difference between the foci and a point on the hyperbola will always be fixed. So I'm going to try to represent that. So let's say we have our y and our x-axis, and here we'll have a hyperbola that is with the center at the origin. So that would be the hyperbola. Now the foci will be just like a parabola. It will be not in between these 2 points, or closer to the center, but it will be kind of like outside each of those branches of the hyperbola. So that will be the foci. And if we were to pick a point on the hyperbola, so it will be on the branches, and we trace the distance, or we calculate the distance from that point to the focus on the left, and then that point, from that point to the focus on the right, and if we subtract those two, we will get a constant number that will match. For example, if I was to pick a point here on the hyperbola, and if I was to calculate distance from the focus to the point, and from the point to the other foci, then those two differences will be constant. And wow, it looks like a parallelogram. I didn't even intend on doing that. So here, let's say that we have D1 and D2, and then here, let's call this D4 and D3. So if we were to calculate the difference between D1 minus D2, and we use absolute value just to make sure that we satisfy the definition of distance being always positive, so that will be equal to the absolute value of the difference between points D3 and D4. Remember, absolute value just because distance is always positive. So that is the difference. That with the ellipse, we use the sum of those distances to compare them. And with the hyperbola, we're going to use the difference of those distances between any point and the foci. And when we say that they are fixed, that means that they will be constant. They will not change. They will be remain constant. They will be equal. So we have here formal definition of the hyperbola. So a hyperbola is the set of all points xy in the plane for which the absolute value of the difference of the distances, which is what we discussed on the previous slide, from two distinct fixed points called foci, is constant. So we already did an example of that. Here you can also see the absolute value and the difference in there. And here is our example. We could call this point point A, and this other point is point B, the points that are actually on the branches of the hyperbola. So those are the points. Here we have our foci, and so we already did a demonstration of why that will satisfy the definition of the hyperbola. So any point that will be on this branch or this other branch will still satisfy that distance, the difference of the distances, and therefore they will be forming the branches of the hyperbola. So we already mentioned that they're called two disconnected parts. They're called branches. And so we actually do have two types. We can have branches going that way, or we could have the other type, just like we did with parabolas or with ellipses. So for example, the one on the left, it's we call that the longest axis. And we also have these points that are called, they're called vertices. So vertices. Let's trace the vertices here. And the line that intersects that, let's use this. So that line is actually called the transverse axis, the one that connects the two vertices. So you could see with the hyperbola on the left side of your screen, the transverse axis happens to be a horizontal line. And so we will refer to this as a horizontal hyperbola just for simplicity. But what we mean is that it has a horizontal transverse axis. So the other one, the transverse axis, is vertical. And so we will refer to it as a vertical hyperbola, meaning that the transverse axis is vertical. Now, the midpoint between the two vertices, it will be considered also the midpoint of the transverse axis, and is actually the center of the hyperbola. Center of the hyperbola. And let's plot that point. So it will be here. Of course, it's not perfect, but on the next slide, you will see a perfect drawing. So that is the center. And the focus, which is not really being mentioned here, that will be on the kind of like the outside of those branches. So meaning that it will not be closer to the center, like the case with the ellipse. In this case, it will be further from the center. So that those points, those represent the foci. Some people call it foci. It's just the plural for focus. Okay, so moving next to the next slide, we have the same terminology here. And so the center sometimes will be at the origin at the point 0, 0, but not all the time. So you need to be aware of that. And we will continue using H and K to represent the horizontal and the vertical coordinate of the center. For the vertices, depending on whether your hyperbola is horizontal or vertical, to find the vertices, we will be adding or subtracting a number, and that number you could already see here is A. In this case, since the horizontal line right here is the transverse axis, we're going to make well, I will rewrite that. Okay, I'll just continue. The horizontal transverse axis. So we consider this a horizontal hyperbola, so that is why the changes are being made to the horizontal coordinate of the center. That's why. If we had a vertical hyperbola, then we will be making the changes, the addition or subtraction to K instead. But right now we stick with H because it's a horizontal hyperbola, meaning the horizontal axis, it has a horizontal transverse axis. What else can we see here? You could also see that when we were discussing an ellipse, we had that the distance from the center to the one of the vertices was considered A, and then we also had that the distance from the center to the foci to one of them, it was considered to be C. And here in this case, C was smaller than A. So with the case of a hyperbola, we're going to have the other case. You could see that since the focus is further from the center, in this case, C is going to be greater than A, with A still being vertex to center. So that is another difference between hyperbolas and ellipses. So I'm not gonna go over this part because it might take me a while. So we're just gonna still consider the length of the transverse axis. So if the length, I'm gonna just try to erase some stuff here. So the length of the transverse axis right here is equal to 2a, just like with the hyperbola. So that length of the transverse axis being equal to 2a, that will help us as well to find once we write our equation to write the standard form. And so here it is coming, the standard form, you can see that. And just to remind you that 2a is also equal to the difference of those 2 points that we were discussing from the beginning of the section. The ones like right here, D2 minus D1. So now let's look at the standard form of the equations. So we do have already discussed the horizontal, transverse axis being horizontal. So what that means, well, before I get to that, I want to point out that the equation of the hyperbola has a minus in between the two fractions, where the equation of the ellipse had a plus. And you can look at your notes if you don't believe me. So what happens here is that the way you will decide which one is horizontal and which one is vertical is going to be based on which variable, in this case is x, is the positive fraction. And I said positive because we don't have a sign in front of it, so it is an implied positive. So that will tell me that we're talking about a horizontal ellipse. Now, For the vertical, of course, it's going to be the other variable. The variable y is the one that it's being, that is first, so it is considered to be positive. So if that is the case, then you know it is vertical. And that's just how it works. And of course, A is going to be the denominator of whatever is dictating the shape of your hyperbola. So if the x is positive, the x squared has a positive sign in front of it, then A will be the denominator there. And so the opposite for the vertical hyperbola. If y is the positive, the y square expression, then a square will be the denominator that goes with y. With the ellipse, it was similar, but just so you remember those little differences. H and K is always the same. They go with X and Y respectively, and they also have a 1 at the end, both of them, ellipse and hyperbola. So if we had the A square here and the B square here, we always say that A is greater than B, right? And that's how you determine if it was a horizontal ellipse, like that, or a vertical ellipse. And if it was a vertical ellipse, it was because the A square was not with the X, but with the Y. I need a little more room. Okay, and this is K. Doesn't look very well. So, you know, all these formulas, it will be very convenient. In fact, I'm thinking that will be the practice assignment for the math lab session that will take place on the 27th. Of course, if you're in my summer 2020 class. So in this case, the A square will be there, and that's how you will determine that you have a vertical ellipse. So yeah, we have the differences with the ellipse. We have positives here, and then whoever has A square, which is larger than B, that's what determines if it's a horizontal ellipse like this one, or a vertical like the one on the bottom. And with hyperbolas, we have to consider which one has the positive sign. That's how we do it. Now, if you happen, sorry, to be lucky and have the center at the origin, then we don't need X and H. I mean, we just need to know that they're equal to 0, but here will be the equations for it. So again, if it's horizontal, A square, well, X square will be the first fraction. And if it is vertical, Y square will be the first fraction. Also, another thing, very important, the way we used to find C with ellipses was different than the way that we do it here. And so if we want to find C square, and we're talking about hyperbolas, it looks almost identical to Pythagorean theorem, right? I mean, it does. So that's how we will find it. So if we were to find A square, then we will be doing the following. C square minus B square. And if we were to find B square, we will be doing C square minus A square. So with the ellipse, the equation was slightly different, and I believe it was a square is equal to c square plus b square. Is it? No, I'm actually going to pause the video and check with my notes. So I did check, and yes, that is correct. And so for this particular equation, remember we're talking about ellipses on the right side of your screen. So for this one, if we want to solve for c squared, for example, that will be equal to a squared minus b squared. So it is very different than the one that we have here. So this is for hyperbola, and the other one is for the ellipse. So please don't get confused with that. I'll write the other one just so you can have all those formulas with you. So if we want to solve for b squared, that will be a squared minus c squared, like that. So make sure you write this down, take a screenshot, whatever you want, but have it handy. So again, the practice will be the formula sheet where you will submit formula sheet for exam 4. Exam 4 is, I will be announcing the dates, but you could submit the formula sheet before it is due. I mean, ideally. Yeah, not ideally, but before it is due, because your exam will happen before or on the same day. Okay, so introduction to the difference on the hyperbolas. So now we've been already discussing how where the focus will be, the foci, I should say, the center and the vertices. Well, here they are explaining to us again, but now the center is not at the origin, as you can see. The center is off the origin in both cases. And then you can see here that we have the transverse axis is horizontal, and so that's why we call it a horizontal ellipse. And here the vertical axis is the transverse axis, so vertical ellipse. So if you were to have to find the foci, then you will use these two formulas, and you will be making the changes to the x coordinate of to the horizontal coordinate, I should say, of the vertex, because it is of the center, I should say, horizontal. That's why. Both cases. But if you have a vertical, so for the vertical hyperbola, we will be making those changes to k, as you can see here. And that is as also, just to find the foci or foci. So that's the difference. Same for the vertices. In this case, if we're talking about the horizontal, we will be finding those points by making the change to the horizontal coordinate of the vertex. So it will be h plus a, comma, k, or h and h minus a, comma, k. For the vertical one, those changes for the vertices will be made to the k. So it will be k plus a and k minus a. And this is to find vertices as well. So I promise you, if you have all of this written and nicely organized, you will be able to work the exam. well, I don't know. I shouldn't promise that. Okay, so we have here finally our first example. And the standard form, it says find the standard form of the equation of the hyperbola with foci at -1, 2, and 5, 2. And so the first thing I just want to do, and also they're giving us the vertices, which is nice. So we have 2 things to work with, or 4. So I'm just going to plot all the points. So we're going to have, let's see, 0, 2. So that will be here. And 4, 2. 1, 2, 3, 4, and then 2. So right there. Then we have the foci, and those are at -1, 2. And the other one is at 5, 2. Right there. Okay, so I'm gonna just mark them so you know exactly those are vertices and those are the foci. Okay, so let's find the center. We have to find the center first. Okay, so the center could be found by calculating the midpoint of either the vertices or the foci, since we have both. So you have options, right? So let's just work with the vertices. So the midpoint is going to be, obviously they have the same y value, so we don't have to worry about it. So the y value will be the same, just a 2. But we could get the difference between 0 and 4. And so 4 minus 0 is 4. I'm sorry, the midpoint. So it will have to be 0 plus 4 divided by 2, right? Like an average of 2 exams. So 4 over 2, it is equal to 2. And that's how I find this coordinate of the vertex. Also, if I was to plot it, you know, just to count, I have from here to here 1, and then 2, 3, 4. So half of 4 is 2. So it will be right there. And that's gonna be our center. Why do we need the center? Well, because here we're saying that h is 2. That looks ugly. H is equal to 2 and K is also equal to 2. And as you know, with the standard form of the equation, we need to have those 2. What else do we need? Well, we also need something that, well, let's see, at this point, do we know if it's going to be horizontal or vertical? So think about it. And I need to know because I need to know if I'm going to start writing x minus something square or y minus something square. So as you can see, if we trace a line between the, oh no, what did I do? Thank God for undo. So if we trace a line that connects the vertices like that, it is horizontal. And so we could say that we're going to have a horizontal transverse axis, and therefore it's a horizontal hyperbola. And so my equation in standard form is going to look like this. It's going to have x minus h squared first as the positive fraction, and then the negative fraction will be the other one, y minus k square over b square, and make sure they equal to 1. And don't pay attention to this, it's just the page number. Okay, so it's equal to 1. That's where we want to get. That's the standard form of the hyperbola. So let's go ahead and find A. So remember that 2A is the distance between the 2 vertices. So 2A is equal to 4. And so A is equal to 4 over 2, which is 2. So now we have another thing. We found, I should write that here. We have that A is equal to 2. Now, what should we do next? Well, we should find C. And so that would be our third step. Let's write it here. So for C, we could use the distance between the foci, and the distance will be the absolute value of the difference, and that will be the absolute value of -6, which is 6, and so that represents 2c. So 2c equals 6, so therefore c is equal to 6 over 2, and that makes c equal to 3. So that is for that comes from the foci. And A comes from the what is it called? The vertices. So that was our third step. And so we have a lot of stuff now. We have our center. So we have H and K. We have A, we have C, but now we need B. And so for B, and that will be our fourth step. To find B, we will be using the one that looks like Pythagorean theorem. C squared equals A squared plus B squared. So if I want to solve for B squared, it will be C squared minus A squared. And well, that's B squared, right? But if I want to solve for B, then it will be the square root of C squared minus A squared. So let's go ahead and substitute that. And that will give us that B is equal to the square root of C squared. So we take C from here, 3 squared. Minus A squared, which is here, 2 squared. And from here we get that B is equal to 9 minus 4. And that will give me the square root of 5. 5 is a prime number, so I know I cannot simplify it. We will just leave it like that so that we have an exact answer, the square root of 5. So from here, we will, now that we know what B is, we could go ahead and, of course, go back to this formula and start replacing things. So we will be replacing of course, H, K, A, and also B right here. So let's do that on the next slide. So we're going to have X minus H is a 2 square over A square. A is a 2, so 2 square. And then minus Y minus K, which is also a 2 square over B squared, so it will be the square root of 5, but then we're gonna square it. So this will be after simplifying it. Oh, and I'm forgetting, this is so important. That is equal to 1. So after simplifying that, we will get X minus 2 square minus Y minus 2 square equals 1 before I forget. And then for the denominators, we'll have 2 squared, which is 4. And then for the square root of 5 squared, that just cancels out, so it's a 5. And that is the standard form of the equation of the hyperbola. So This one right here is the final answer in standard form. Oh, and we actually have the graph right here. So you could see the points, the vertices were given to us. Also was the foci. And then after that, we were able to find the vertex, not the vertex, the center. The center, yes. Now, we cannot graph that unless you're using a software, a graphing software or calculator. We cannot graph it by hand yet, but we could. And the thing that we are missing is how wide the branches will be opening or how narrow. So what we're gonna do here is start talking about two other points. And for example, those 2 points will be the square root of 5 away from the vertex, I'm sorry, from the center, above and below. And so what I'm going to do is, well, try to calculate the square root of 5. Okay, so the square root of 5 is approximately 2.23. So those 2 points will be like 2.23 units. And let's see if this is 1, this is 2, this is 3. So from the center, so it will be 1, 2, and then like a little bit more. So like right there. And then also below the vertex, the center. So 1, 2, and then that 0.23, like right there. So what we do when we graph this like with a pencil, so on your final exam, you might be required to do this because that will be on paper. And so we trace this little box from the vertices and from this point over here as well. And we could, of course, I expect you to use a ruler. We connect, let me use a different color. We connect the points of that box, of course, going through the vertex like that. And in fact, those are going to be the asymptotes that we're going to learn how to find in a minute. Because if you extend those, oh, I don't want to do that. If you extend those lines, then you know exactly how to graph your hyperbola, because your hyperbola cannot go across those lines. So in fact, we should have arrows at each endpoint, but yes, so that's how you can get a perfect drawing of a hyperbola. So let's move on to how to find those asymptotes. So we have here asymptotes of a hyperbola. So like I mentioned earlier, each hyperbola has asymptotes. Here's that little box that we made. Here. Here are my vertices. And I guess we could call this ones like not vertices, but they are kind of like if they were like the points on the minor axis, on the one that is not the transverse axis. So we made a box, and then the asymptotes come this way. Now there's an algebraic way to find them, and that is with using, by the way, before we get to that, the points that we have here, let me use a different color. Let's use this one. So these 2 points, those come from the distance of B. And that's why I used the square root of 5, because that was the distance, that was b square right here, meaning that b was the square root of 5. That's what we found it to be. You can see it here. So that's why I positioned those points above the center and below the center. They're on the axis that is not the transverse axis. And so the distance from each point to the center, it's b. So that's why if you put them together, you get 2b for this axis. For the one that is the transverse axis, it will be a and a. And that's why the distance is considered to be 2a. So to find those points, the ones that are not the vertices, but they help shape that box, we will be using the formulas that you see here. And if for a horizontal parabola, the change will be made to the vertical. Because remember, for the vertices, we do the change to the horizontal. Like that. And so for the other points, we do the change to the vertical. Now, if the situation was reversed, in the sense that we had a vertical parabola, hyperbola, I'm sorry. It's just they all have the similar names. So if the case that we had a vertical hyperbola, oh, and actually we have a name for it. It's called the conjugate axis. The one that is not the major axis is the conjugate axis. That's the one with the length 2b. So if we had a vertical hyperbola, then the changes to find those points on the conjugate axis will be made with the horizontal coordinate, because remember, for a vertical hyperbola, to find the vertices, you do the change to k. So all those little formulas are going to be so important when you do your homework. And the homework is not too difficult, but you do need to have an understanding of what are the formulas and what they represent. So how do we find the exact asymptotes? So to find those, you could see very clear that they are straight lines, right? So we could consider them linear functions. And they are not part of the hyperbola because there are dashed lines. They're not solid lines like the branches of the hyperbola. So the way we find them is with the formulas that you see here. So if we had the easiest case, the ideal case, when the center is at 0, 0, then to find those hyperbolas, it will be so easy, because if we had a horizontal hyperbola, we will just need we wouldn't have to worry about h and k. We will just use b over a positive and b over a negative. That's it. If it was a vertical hyperbola with the center at 0, 0 as well, then to find those asymptotes, those lines, the equation of those lines, it will be a over b, and also positive, and also negative a over b, and that is negative. So and that's, the ideal case, but of course that doesn't happen all the time. So if you do happen to have a center that is not at the origin, and this will be with the center at hk, then what will happen is that you have to follow this formula. So for horizontal, you will consider k and h, and for vertical, same thing. You will consider K and H. Now the plus minus that you see here, it means that we have one of each, one with a positive sign and one with a negative sign. So it will be two different operations. So we're gonna find those on the next one, because we're gonna sketch the whole thing, the whole hyperbola. Example 2. We are going to use the asymptotes to sketch the hyperbola. So first thing is to transform the equation that we have here into a standard form. So remember that we want to have a 1 on the right side. So how can we get that? Well, by dividing every single thing by 16. So of course we will have 4x squared over 16. And then here we will have minus y squared over 16 if we split the fraction. Then we will have 16 over 16, which is equal to 1. We could simplify this part right here, because 4 and 16 can be both divided by 4. So 4 divided by 4 is a 1. So we will have 1x squared. And then over 16 divided by 4 is a 4. And then we have minus y squared over 16. So here we already know several things. First of all, the center is at 0, 0, which is great because h and k are zeros. Then we know that a squared, it now is not the biggest denominator, it's just simply the positive denominator. And so that will be, or not the positive, but the one with the positive fraction. And so a squared is 4, which tells me that a is the square root of 4, the positive one, and that is 2. Positive because we're talking about distance. Then we know, so that was the second thing we knew. Third thing is that we know that b squared is equal to 16. So then b is the square root of 16, which is 4. And what else do we know so far? That's it. We will find the focus just so that we know where to position. I mean, we will find C just so that we know where to position the foci. Okay, so we're going to use the equation c squared is equal to a squared plus b squared. Then so c will equal to the square root of those two, a squared plus b squared. And we are going to get c is equal to the square root of a square is a 4, remember from here, and then b squared is 16. So from here we have that c is equal to the square root of 20. Now WebAssign might want you to enter, if they ask for the value of c and they wanted an exact answer, you may have to simplify this root as 4 times 5, which is the same as the product of the square root of 4 times the square root of 5. And so we take the square root of 4 as 2, and then the square root of 5 stays in. So that would be the exact value for it. But of course, you know, they might ask for an approximation and then specify how many numbers they want you to round that to. So you enter that on your calculator, and I'm getting an approximation of 4.47, just rounding it to the nearest hundredth. So that would be the value for C. And you know that is important because of the foci. So let's write the points that we're going to have. And I believe those points are going to be, for the center, we already have it. For the vertices, since we are talking about a horizontal hyperbola, because the horizontal axis will be the transverse axis. And also let's point out that our vertex, our center, I should say, I keep saying that, is at the origin, 0, 0. So there it is. Now, for the vertices, we are going to use the formula that says h plus minus a, comma, k. So what does that mean? That we have two of them. We have 0 plus the value of a, which is 2, so that's just a 2, comma, the value of k, which is 0. We also have negative a, or h minus a, which will be 0 minus 2, which is negative 2, comma, the value for k, which is 0. So those are the vertices. Let's plot those. So they will be at 2 units from the center in each direction, left and right. So there will be here and here. Right there. Now for the foci, let's go ahead and use the approximation. And those points will be at 4.47, comma 0, and also at negative 4.47, comma 0. So let's plot those. Okay, so those, I'm gonna plot them in blue. Okay, so something like that. Now let's find those points that are on the conjugate axis, the one that is not the major axis. So in this case, vertically, those extra points, and those come from B. Where is B? Right here, 4. So what we're gonna do in this case is use the formula H, comma, K plus minus B. So those points are gonna be 0, comma, 0 plus b, so b is 4, and the other one is gonna be 0, comma, 0 minus b, so negative 4. So those points, let's put them over here. Here. And here. And you could see now that the conjugate axis happens to be longer than the transverse axis. That's fine. That's okay. It just may happen. So now one thing we could do is trace that little box from those places. And then we could, I don't want to make them solid, so trace those lines. Those are the asymptotes, but of course we need the equations. Okay, and so our parabola is going to, of course, has to touch the vertex, but it's not going to go across those asymptotes. And I mean, I know my drawing is not that pretty. So the hyperbola, I think I called it the parabola again. So it goes like that. It gets like dangerously close to the asymptotes, but it does not touch them. So again, from this vertex, we go in that direction and in this direction. Now, of course, we need more precision, right, to find some points. So you could always find a random value for x and then try to find what the y value will be. Or you may pick a value for y and find what the x will be. So that's up to you. So now to find the equations with the actual formulas, remember a is 2 and b is 4. So I'm going to go here because we have a horizontal hyperbola with the center at 0, 0. And so we say that a was equal to 2 and b is equal to 4. So my first asymptote is going to be positive b over a using this formula, and that is equal to 2. So my line is going to be, I shouldn't write it that way. My line will be y equals 2. Now for the other one, we will use this formula. So it's going to be y equals negative b, so negative 4 over a, which is 2, and that will be negative. That means that y will be equal to negative 2. So that is what we're going to use. And actually, I'm forgetting the x because they're linear functions. They're linear functions. So they should have an x right here. So please add that to your notes. They're not just horizontal lines. They're slanted lines, right? They do have an x, just like this one's have an x. I should have put an x there. So my two asymptotes are going to be positive 2x and negative 2x. Those are the two asymptotes. So if we needed to trace something like that, super precise, the equation of this one, the one that is leaning to the right, is y equals positive 2x, and the other asymptote is y equals negative 2x. Now remember, here's with the center at 0, 0. So if the center is somewhere else, then you will need to use the formulas that you have listed here. When the center is not at 0, 0, is at hk. So any other number that is not 0, 0. So right here, it was for us to graph it. Let's just, trace it again. So you connect your lines, and those should be dash. And then the hyperbola will start from the vertex and extend in that direction, in both directions, like that. Okay, so just like ellipses, we have the eccentricity of the hyperbola, and the formula to find that is c over a. And c, and because c is bigger than a, we discussed that at the beginning, the distance from the center to the focus is greater than the distance from the center to the vertex from one of the vertices. So that's why c is bigger than a, as you can see on this examples here. So it follows that if you divide a bigger number by a smaller number, you will get a result that is greater than 1. Unless the two numbers are the same, which it wouldn't be a hyperbola, but so you will get a number that is greater than 1, not a fraction less than 1. So with the larger the eccentricity gets, the more the branches of the hyperbola will look flat like a line. So you could see here we have if we were to divide c over a, it will be a large number. And so, like if you had I don't know, a hot dog that was this long, and you cut it into pieces that are this little, you will get a large number, a number well above. Let's just estimate 1, 2, 3, 4, 5, 6. You will get a 6. So let's consider that that is a large number. So you could see the branches, they almost look like vertical lines. Not really, But the larger it gets, like if I imagine if it had an eccentricity of 10, it will of course be even flatter. So if the eccentricity is smaller and the closer and closer it gets to 1, then the branches of the parabola, instead of looking very open, like almost like open arms or like lines, they start looking more narrow if the eccentricity is smaller, close to 1. So that will be a difference. Might be a question on the homework. And so for our last problem, we have this example 5, and it does say 2 microphones are 1 mile apart. The record record an explosion. Microphone A receives the sound 2 seconds before microphone B. Where did the explosion occur? So assume that sound travels at 1100 feet per second.
I was listening to a podcast